Sam, may I start? Sam, may I start?
Yes, Steve, please go ahead.
Okay. Good afternoon, and welcome to an overview of liquefied natural gas. This is an Insight professional continuing education course. Insight is a premier provider of continuing education for professional engineers as well as for other professions. And I bring this up because this is the place to go when you need continuing education credits. I'm going to tell you a little bit about myself before we get started. I have a lot of background in engineering. I have a bachelor's, a master's degree, and a doctorate degree in mechanical engineering, civil engineering. I have a master's degree in civil engineering, and I was taking nuclear engineering when the university asked me. I was leaving class at night, and they said, "Would you like to teach here at night instead of take classes?" And I said, "Let me see if I understand this. You're going to pay me instead of me pay you, and I come here and I still learn?" Yep. So I said, "I think we can make this work." So I've done a lot of education as far as engineering, worked the theoretical end, but I've also worked in the gas industry for 53 years. And you'll see a common thread throughout my presentation of safety. And I'll give you a little bit of history. In my end of my first year of working in the gas industry, my boss, who was also had become friends, he became my role model, and he was working a job, and I asked him to stop off. He was working a Sunday job, and I asked him to stop off at one of my jobs to check on the pressure test I was running. Well, I called his house that afternoon, and his wife was on the phone. She was frantic. She said, Steve, my husband is on the job and there's been an explosion." And I said, "Look, I'm sure everything's fine." She couldn't get through to the dispatcher. And I said, "I'm going to drive down to the job and have him call you." Well, I drove down to the job and he was dead, taken to the hospital. Six people were overcome uh, by nitrogen and natural gas. And of those six, five were revived. He was not. Uh, a couple of months later, and that was quite a shock in my life. But a couple of months later, I'm in the office. I receive a phone call. Steve, another worker from the job site. He was frantic, and he said, "There's been an explosion on the job, and two men were killed." And this was the start of my career. So from that point on, I've made it a point to always investigate accidents that occur in the operation, and even if it's outside of my area of expertise. I left the gas industry as vice president and chief engineer, and part of the job I took on was to go to other departments outside of my responsibility and give them classes before the crews would roll out, to give them an awareness of this, the importance of safety. And a lot of times it boils down to one thing: engage the brain before you take your foot off the clutch. And I'll give you an example. Like shortly after this, I was in maybe a year after this occurred with my boss. I come up to a job, and a 2-inch pipe had been pulled out of the ground, and a 60 psi pipeline was blowing gas. I jumped into the opening, grabbed a stick, wrapped the rag around it, and shoved it into the pipe, stopped the gas from flowing. Well, what do you think happened? What's the area of a 2-inch pipe? Pi r squared. R is 1 inch, squared is 1, times pi is 3.12 times 60 psi. It's 180 pounds force on that stick pushing it out. As soon as I stopped that gas and the pressure built up behind it, boom, I got thrown across the trench, and realized I was not stopping that gas. I climbed out. Now, when was my company in liability? When I stepped into the trench. When was there a real hazard? When I stepped into the trench. What did I fail to do? Engage the brain before taking my foot off the clutch. I reacted rather than thinking first. And if you think about it, there was no real hazard. Even if it caught fire, there's nobody in the trench, and we have a big fire. You make an opening away from the trench, shut off the gas supply, the fire goes out. So my key in this presentation will have a string of safety requirements as I go through it. Let's talk about LNG. Why do we want to know about LNG? What is it? It's liquefied natural gas. How do I take LNG? Let's say I have a container that has natural gas in it. I'm showing you a cup, but let's say it's a container that has natural gas in it, and I chill it down. Well, as I chill it down, it gets more and more dense, and then eventually becomes a liquid. But there's a problem with just taking natural gas and doing that because there are some things that'll freeze up on your heat exchangers, like CO2, water vapor, H2S, heavy hydrocarbons. So you have to clean it up. That's called pretreatment. You clean up the natural gas and then you can refrigerate it. And how do you refrigerate it? The same way you do air conditioning. You use a refrigeration process. Now, can you do it in a single refrigeration process? Not really, because you have to go from ambient temperature that your gas is at all the way down to minus 260 degrees Fahrenheit. That's approximately minus 160 C. We'll talk about liquefaction systems, LNG tanks. LNG tanks are nothing more than highly insulated tanks. Talk about valves, pumps, vaporizers, and other equipment. Bog is something you'll hear me talk about quite regularly, quite often. Bog is boil off gas, and bog happens continuously. Why? Because we're not continuously refrigerating the LNG, and heat is always leaking into your LNG tank. So heat is leaking into your LNG tank. The LNG tank is continuously boiling off. We'll talk about how much is boiling off per year. You lose about 18% of your LNG just by boil off by heat leak going into your tank. That's something to remember up here, because it might be on the exam. That's about 0.05% per day. 0.05% times 365 days gives you 18%, actually 18.25. Bog management, plant operation, and we can also talk about transporting LNG, which can be done by either truck or by ship. Some of the general characteristics about LNG, and we'll talk about LNG safety. And I bring this up. This is a picture of my granddaughter. She's a bit older now, but I bring this up because everybody on your job, whether it be the crudest, roughest, toughest operator or mechanic, or whether it be the engineer with the fancy suit or the executive, everyone deserves to come home at the end of their day healthy, without injury, and certainly alive. And everybody has someone that loves them, or someone that they love, and they need to come home at the end of their shift. That's something I put up here for you. Something to remember. It's only when you lose somebody that you've worked with for a long period of time do you realize that that bond of closeness that you have working together rips a piece of you out when that person gets injured or gets killed on the job. And part of that involves also people that have been disabled through injuries. And I know many of them over the years. Let's talk about some definitions. I'm not going to go through this long list of definitions, but I do want to bring out certain things. PSIA and PSIG. PSIG is gauge pressure. I go to the store, pick up a gauge, and it's reading 0. And I think everybody talks about, oh, it's 0 PSI. So I put it on a pipe. What's the pressure in the pipe? It's 0. Not true. The absolute pressure is we're in a pressurized atmosphere. So the absolute pressure is 14.73, 14.7, depending upon where the barometer is. But in reality, we have been used to reading our tires 30 psi. And we're thinking that's what's in our tire. What's actually in our tire is 34.7 psi. And then the outside of the tire is 14.7. So every single gauge that you get and read is a pressure differential gauge, not really a gauge that's just registers the pressure. It's a differential pressure gauge. It's measuring the pressure from some base point It could be zero, in which case that would be an absolute pressure gauge, or it could be falling 1 atmosphere, the air that we breathe in, as being the 0 point. So if I took that gauge and went up to outer space, the needle be reading below zero. That 600-pound gauge. Now, on a 600-pound gauge, it doesn't really matter because we're talking about a very small amount compared to 600 psi. But let's say I was reading the pressure in an LNG tank, which is only 2 psi, and let's say the barometer has changed a half a psi. Well, now I'm getting a very severe error in my reading. So that's what I'm talking about, gauge and absolute pressure. Pound mass and pound force. I happen to be about 174 pounds mass. Whether I'm on Earth or on the moon or out in outer space, I'm 174 pounds mass. When I step on a scale, though, it pushes down on the scale with 174 pounds force, not mass. Because if I step on the scale in outer space, I read 0 force. If I step on the scale on the moon, it's about 1/6, so I'd be a little bit less than 30 psi if I stepped on the scale on the moon. So, you could see the difference between pounds mass and pounds force. In the industry, the gas industry, we talk about a standard cubic foot. And a standard cubic foot sounds like a volume measurement, but in reality, it's a mass measurement. Why? Because if I give you a cubic foot, you can't tell me how many molecules are in it. But if I give you a cubic foot and tell you two intensive properties of that, of what's inside of it, and an intensive property is a property of the fluid that does not change when you change the volume. So if I tell you two intensive properties like pressure and temperature, I can now define how many molecules are in that cubic foot. So I say a standard cubic foot of LNG, not of LNG, of natural gas, is so many molecules of it, and you can calculate it out. And why do I know that? Because that standard temperature and pressure. But I caution you, everybody measures standard pressure and temperature difference. If you go to a college, a university, well, now they'll teach it in SI terms, but in the gas industry, they tend, in the United States anyway, they tend to stay with the English terms. So 14.73 and 60 degrees Fahrenheit is SDP, standard temperature and pressure, in accordance with the American Gas Association. But if you have an EPC contractor come in and build a LNG facility for you, they will use 14.696, which is what you typically learn in university, and 60 degrees Fahrenheit. If you trade gas on Henry Hub, where they trade gas in big bulk quantities, they'll be using 14.73 and 59 degrees Fahrenheit. It's something different. So if you import LNG that's coming off of a ship from Algeria, they'll be talking some different. They'll be using SI units, but a different standard temperature and pressure. The key here, the reason why I'm bringing this up is because if you're dealing in energy units and you don't get this right, and you're dealing in large quantities, talking about millions of dollars lost just by defining a standard cubic foot differently. And what about a BTU? We think a BTU is a fixed amount of heat energy. No, it isn't. And here's why. BTU is the amount of energy it takes to raise 1 pound of water 1 degree Fahrenheit. But I ask you a question, at what temperature? Because if it's at 60 degrees, your specific heat of water is a certain amount. If it's at 39 degrees, it's different. Different countries and different industries use different standards for measuring a BTU. So standard cubic foot is not standard. A BTU is not standard. Higher heating value, which is the amount of energy you get out of a cubic foot when you burn it and bring the products of combustion down to back down to standard conditions, that's not an accurate measure either, unless you all agree, every party agrees to what your SDP is going to be. By definition, a therm is 100,000 BTUs. Now, the gas industry is a little bit of an oddball in its measurements. We use a decatherm, but it's spelled DEKA, and everyone else uses deca, DECA. So if you say decameter, a decaliter, but in the gas industry, we use DEKA, a decatherm. And the difference is one is derived from the Greek and one is derived from the Latin. I believe the DEKA is from the Latin and the DECA is from the Greek. I'd have to look which one is which though. The other oddity about the gas industry and its measurements is that everywhere else or every other industry uses K to mean 1,000, not in the gas industry. In the gas industry, we use M to mean 1,000. So if I said 1,000 decatherm, it's an MDTH. Or if I said 1,000 standard cubic foot, it's an M standard or MSCF. 1,000 standard cubic foot. Now, many people in all other industries will use M to mean 1,000,000, but in the gas industry, it's 1,000. So how do we say 1,000,000 standard cubic foot? It's an MMSCF. Kind of strange, but that's the way it is. A BCF is where we change to normal nomenclature. We call it a B standard cubic foot. So it's a billion. A gallon is an imperial unit, about 7.48 gallons in a cubic foot. And another type of measure that we use, especially in transporting LNG, is a cubic meter. Then there's a normal cubic meter, very similar to a standard cubic foot. It's at normal temperature and pressure. Then there's a barrel. There's two types of barrels. You have a wine barrel, which is 32 gallons. You have a petrochemical barrel, which is what we use in the LNG industry, and that's 42 gallons. So if I said I had an LNG tank that was 1,000,000 barrels, that's 3.3 billion standard cubic feet or 42 million gallons. Then here's some approximations that you might want to keep in the back of your head or keep as a reference. I put them there. We manage a lot of energy. Let me give you, for instance, most LNG tanks are in the order of magnitude size of a 1 BCF. Now, import and export terminals, they may have 3 or 4 BCF per tank, big tanks. But most of the peak shavers, and I'll explain what a peak shaver is use about a 1 BCF tank. Well, that's about enough fuel to heat your house 24 hours a day, 7 days a week, for about 1,000 years. It's enough energy for you to drive your car around the world 6,600 times. Each average size LNG tank, that was what I just mentioned, was 1 BCF. An average LNG tanker ship carries 3.4 BCF. A cubic foot of LNG cubic foot, of LNG, when you vaporize it, grows to be 600 standard cubic foot of vapor. 1 gallon of LNG is about 80 standard cubic foot of vapor at STP. You and your coworkers deal with one heck of a lot of energy. So I mentioned the word peak shaver. And what's a peak shaver? Well, let's say we live in the Northeast, and many of you are from New York. So let's say you live in New York. Where does the gas come to? Come to you from New York, for New York. Comes from Texas, most of it, Texas and Louisiana, and about 20% of it comes from Canada. And you may not, the gas you actually see may be all from Pennsylvania. But even though it's coming from Texas, Louisiana, you're buying it there, it's stored in Pennsylvania, shipped during cold weather. So the whole natural gas grid is a grid that everybody's inputting and other people are taking off. Whose molecule you're actually getting doesn't really matter. Down in Texas, they may put in 300 million molecules. Up in Canada, so many. You are pulling off of this grid. You may have a contract with a company in Texas, but in reality, it doesn't matter. You're just taking off the grid, I call the grid, but it's really a pipelines. But what happens on the really real cold days, like when it's 0 degrees outside, You can't push enough gas through that pipeline. So you have storage facilities, which are essentially uh, pieces of they're essentially underground storage capabilities that allow you to pump gas in during the summer and then during the winter take it out when you need it. So that's a peak saving facility does that with LNG. During the summer, you liquefy gas, you liquefy it, and you store it in these tanks. And then during the winter, you then heat it up and send it out as vapor. So it's a supplemental supply of gas supply. And in the United States, there are about 71 peak shavers. Now, 48 of them have liquefiers, but by FSMA definition, peak shaver has a liquefier. All that means is that it's reported wrong. This is the actual reported data. 48 have liquefiers, but by definition, they should all have liquefiers. A satellite facility would not have a liquefier. And you can see there are 23 satellite facilities, yet one of them is listed as having a liquefier. So that technically would not be classified as a satellite facility by definition. But this is actual data that's reported by the companies to FSMA, and FSMA has this data available. If you ever, the link I left you up there allows you to go onto the FSMA site and take out that or download this information. And I'm not moving fast enough, so let me move kind of get myself in higher gear. Where does gas come from? The easy gas comes from conventional gas wells, where there are pockets of gas underground. Then there are conventional associated gas wells. This is a gas well that has both oil and gas in it, and you have to separate them. And in the beginning of the industry, they used to be always looking for oil. Gas, nobody sold gas. It was a nuisance to the oil drillers. They would drill, they'd hit gas out, burn it off, and get down to the oil. But now, in around the 1950s or very early 50s, pipelines were spread from Texas and Louisiana up the east and west coast, and all of a sudden, natural gas became available to places like Baltimore, New York, Boston, etc. And since then, those pipelines have been expanded, and the sale of natural gas has become a massive industry. In fact, 1/3 of the energy used, that's an approximation, is natural gas. And that we're converting many of the oil and coal-fired electric generating stations to natural gas. So demand for natural gas has increased. So much so that new technologies have been used. And one of those technologies is directional drilling. There's a lot of gas that's locked up in shale, and that's a rock formation. And the way they get at it is they horizontally drill through that shale, frack the shale, and then they extract the gas out of it. And they're only extracting about 10% of the gas that's in there, but that's so much. You see, it's a tremendous amount of gas. So in new future technologies, maybe they'll learn how to extract 20%, 30%. There are tremendous amounts of gas hydrates under the ocean. They don't know how to extract that yet, but I'm just saying there's plenty of gas. How do you frack a well? Well, typically here's a well site, and there'll be 6 pipes coming down, spread out, 3 in this direction, 3 in the other direction, and then they will block it off and explode pellets or bullets through the piping, which now puts holes in the piping. Then it pumps down very high pressure water, which fracks the gas, fracks the shale. And fracking means cracks the shale. And in that water is sand droplets. It's those sand particles that keep the cracks open. So that when you then extract the water, the gas that's in the shale follows it and goes up with the first you get the water out, and then you start getting gas, and it keeps coming and coming. And I've been on a couple of these shale sites, and they're amazed at how much gas comes out of the shale. It just keeps on coming. So this has been a revolutionary technology. So how does gas transport? Typically through pipelines. This is a FSMA map of the major pipeline network in the United States. This is transmission piping. There's about 300,000 miles of transmission piping and about 1.3 million miles of distribution piping. Distribution piping is the pipe that's outside front of your house that delivers gas to your house. Transmission piping is the high pressure piping that takes the gas from the production centers up to the high use centers, or what we call the load centers of New York, Boston, Baltimore, etc. LNG is nothing more than natural gas that has had its contaminants taken out and then chilled, and it becomes about 1/600th of the size, and that's why it's stored as the LNG because it's a very dense concentration of energy. When is LNG used? It's used when there's not enough gas coming up the pipeline, and you now have to supplement the pipeline supply with vaporized LNG. How do you vaporize LNG? Take the LNG, add heat, turns back into a vapor, continue heating it till it's around 40 degrees Fahrenheit, and then you put it into the pipelines, goes out to the customers. And customers don't see any difference between natural gas and LNG. The only thing that happens, though, you have to do is when you liquefy it, you're actually taking the smell, the odorant out of the gas. So you have to put odorant back into the gas. When is it used? When there's not enough gas coming up the pipeline. And also, when you want to take stranded gas, let's say I have this great gas supply, let's say it's in Alaska, and you want to get it to some other country. Well, how do you get it there? Well, you put it on ships. And in fact, the first LNG facility in the United States, export facility is in Kenai, Alaska, and it was to take LNG from Alaska and ship it to the east the Pacific Rim countries. I'll call it that without knowing what the correct terminology is for those countries, but I'll call it the Pacific Rim countries that need natural gas. As for instance, Japan, a major industrial country, has no indigenous natural gas. They import every drop of natural gas in the form of LNG. LNG is used when there's not enough gas and also when you have to move stranded gas to other locations. What is a major component of LNG? What's the major components of natural gas? Major components are methane, typically over 90%, ethane, 3 to 8%, propane, around 1%, even some nitrogen. Typically, natural gas will have a little bit greater than maybe up to 1 to 2% nitrogen. LNG will typically have, when you first make the LNG, there will be some nitrogen that is liquefied, but for the most part, after a couple of months, all of that nitrogen has boiled off preferentially. So it's flammable. If I took 1 cubic foot of LNG, it would produce about 630,000 BTUs of energy when burned. And you think about it this way, a cubic foot of natural gas is about 1,030 BTUs of energy when burned. And 1 cubic foot of LNG makes 600 cubic foot of vapor. So that's where I get this 600 to 630 uh, 630,000 BTUs. 1 cubic foot makes 1,030. 600 cubic foot makes 663,000 BTUs of energy. It's a 600 to 1 ratio, essentially. LNG is odorless, so you have to watch out. Nitrogen is odorless, so you have to watch out. I say that intentionally because if you're in an environment where there's low oxygen concentration, you will pass out, and if it's low enough, you will die. I remember interviewing the people who were overcome by the nitrogen gas environment, the 5 people that had survived that accident, and many of them said they pulled their shirt up over their face and went in to help their fellow workers who fell. And there was originally 2 workers that fell, 2 others jumped in, pulled their shirt up. Pulling your shirt over your face in a oxygen deficient environment does nothing. And that's a myth that people don't realize. There are a couple of other myths, and that is that, well, LNG vapor is nothing more than natural gas. Natural gas is lighter than air, so LNG vapors will rise up into the atmosphere. I've heard many PR people from the gas industry say that. It's not true. Here's why. The LNG vapor is so cold that it's dense. It's actually denser than air. And it's minus 260 degrees Fahrenheit when it boils off. So you have the liquid at minus 260, you have the vapor at minus 260, and as the vapor travels, it's hugging the ground until it warms up. When it gets to be around minus 150 degrees Fahrenheit, just about buoyant with air. Then you warm it up, it gets warmed up more, and then it becomes buoyant with air. So the density of LNG is about 27 to 29 pounds per cubic foot. If I have a cubic foot of LNG, put it on a scale here on Earth, weighs between 27 and 29. Now, why the difference? Based on the composition. It's got a lot of methane. It's going to be very light, more like 27 pounds per cubic foot. It's got a lot of heavies, ethane, propane, a little bit of butane. Then you'll have a heavier mass. And what's specific gravity? It's the mass of whatever you're measuring divided by the mass of water, the density of water. What's the density of water? About 62.4, 62.4 pounds per cubic foot. Divide 27 by 62.4, we find the specific gravity of LNG is about 0.45. And why is this important? Because when you're shipping it across a ocean liner, you have to realize that the weight of your LNG is much lighter than the water that it displaces. So you use your ballast to make sure your ballast is how much water you take on in the ship to keep the ship at the right elevation in the water. Produces bog continuously. That's one of the things. Why does it produce bog continuously? Because you continuously have heat leaking in. Bog is heavier than air, but specific gravity of natural gas is about 0.6. That's at 60 degrees Fahrenheit. So natural gas and bog have been brought to STP properties, have a density of, LNG would have a density of, let's say I take natural gas and I take a standard cubic foot of it. It has a density of about 0.045 pounds per standard cubic foot. And that's a standard cubic foot of natural gas. Standard cubic foot of air is about 0.076. If you divide 0.76 into 0.045, you get a 0.6. That becomes your specific gravity of natural gas. Why is this important? Because you're understanding the relationship between natural gas, air, and LNG. If I take this 0.045, this is a standard cubic foot of gas, and I divide it into this, pick 28 as the number, what do you think I get? About 600 to 610, which is the ratio between natural gas and standard cubic foot. It can cause mechanical explosions. If you have LNG, it's a liquid that wants to boil off by heat absorption. RPT is a mechanical explosion, rapid phase transformation. What it means that if LNG is spilled on water, it will spill on water and vaporize very quickly. In some cases, it'll vaporize so quickly that it will cause a mechanical explosion where the heat transfer is so high into the LNG that it'll expand so rapidly, it expands as an explosion. Mechanical explosion, no combustion, just a boom. And I have a picture of that I'll show you in a little while. Can natural gas, LNG, liquid natural gas, can it blevy? And think about what a blevy is. We all think of a blevy as a propane container that's been overheated. Top of the container gets soft because of the heat, and there's no liquid there to take the heat away. It gets weakened and blows up, and all the liquid inside the tank expands and vaporizes, and you get this tremendous explosion. Well, you can have that happen with a steam boiler also. You can get a blevy. Just don't have you just won't have that secondary explosion of the chemical reaction. But when an LNG pipe or vessel, if you disconnect it or separate it from its relief valve, the pressure will build up, build up, build up. Why? Because it's continuously gaining heat from the environment. And if you have, let's say, you had a pipe and you had a valve closed and a valve closed, and the relief valve is closed, well, that will continuously gain heat and eventually, boom. And then if it finds a source of ignition, you'll get a secondary explosion. Typically, it won't have a difficulty finding a secondary, a source of ignition because the first burst is so powerful that it'll rip out, let's say it's in an LNG facility, it'll rip out all the electrical conduits, other pipelines, and things like that. And that's what happened at the Freeport facility in Texas. So LNG can levy. How do you make LNG? Well, we have to take out some of the contaminants. What are the contaminants? Those that'll freeze. So let's say I have a pipe and I start putting cold stuff, whatever that stuff is, through the pipe. And I look at the pipe and okay, let's say I fill the room with with natural gas to start off, and I put a cold pipe and I start putting cold stuff through this pipe, and I start seeing, first thing I would see is, well, look, there's some droplets coming off the pipe. What is that? Oh, it's water. As the pipe cools down, any water vapor that's in the air, that's in this gas might drop out as a liquid. Then all of a sudden I see it frosting on the pipe. What's that? I scrape it off. Oh, that's liquid ice. Or that's not liquid ice. That's water that formed into ice. Let's say I say, okay, let's dehydrate the gas in the room. Take all the water out of the room. Now I make the pipe colder, colder, gets down to minus 105 degrees Fahrenheit. I said, doing great. Get that pipe down to minus 108 degrees Fahrenheit. What happens? I start seeing ice again. Now I take that ice, scrape it off. It's CO2. It's dry ice. So now I have to take all the CO2 out of the room. Okay, so now I take all the CO2 out of the room and I can go through this process again. H2S, small trace amounts of H2S are in the gas, very poisonous gas, but that has to be removed as well. And heavy hydrocarbons such as pentane, in particular benzene, toluene, xylene, those chemicals will freeze up in your heat exchangers, even if they're at as low as 1 part per million. So you really have to get rid of the benzene, xylene, toluene, and the ethylbenzene, those H6 components. And what do you have left? You have basically methane, ethane, propane, that becomes your LNG. Because it'll corrode, you also have to take out mercury. There is a small amount of mercury in LNG, not in LNG, I'm sorry, in natural gas. You do not want it in LNG because all of your heat exchangers are made out of aluminum. And they're made out of aluminum because it's a cryogenic material. We didn't talk about why materials have to be cryogenic, but we will very shortly. Now, I say it's a cryogenic material. Typically, anything colder than minus 100 degrees Fahrenheit is called cryogenic. And what it means is very cold. So what happens if I take a carbon steel, let's say a pipe, and I bang it across a tree, and the pipe may dent, the pipe may bend. It's going to be a ductile pipe. It'll bend, it'll dent, it'll keep its form as a pipe. But let's say I dip it in LNG. And let's say it doesn't crack yet, and I take it out and I smack it across a tree, it'll shatter because it's become very brittle. So regular carbon steel cannot withstand natural gas that's been liquefied because it's too cold. Then you have to use special steels, 9% nickel steels, certain stainless steels, certain aluminums. So your heat exchangers are made of aluminum. Those certain aluminums that can withstand the cold temperature. And aluminum is a great conductor. That's why you use aluminum to make your heat exchangers. But if I put a drop of mercury on an aluminum plate and then have this presentation, by the end of the presentation, I could show you that drop of aluminum, that drop of mercury has corroded a big gouge in that piece of aluminum. So you got to take out the mercury as well. LNG vapor and combustible mixtures. We're going to talk about that next. Now, this is an AI screenshot. And I want to put that there because I didn't have, go back one. I didn't have a, I do have an actual picture behind me, but it's not one that I had rights to. So I just put over an AI picture. It just shows that natural gas, when it vaporizes, you see a white cloud. Now, what is the color of the vapor? It's not white. It's clear. You see right through it. What are you seeing when you see a cloud from a vapor cloud that comes off of LNG? You're seeing the water that's in the air condensed. So what you're really seeing is condensed water vapor in the air. So the actual cloud of vapor is odorless and invisible. But what you see, because it's so cold, you get to see this cloud of water vapor. The cloud hugs the ground. That's the important thing to remember. And then when it finds a source of ignition, you have a fire take place. Here's a fire. And this happens to be at a test facility. And this is, I can share this because this is off of a government's website, and it's government, it's public domain. Now, you're in an LNG plant, you always look at the windsock, see which way the wind is going, because all of the theoretical work that's done is based on certain wind conditions, and you'll see what's called isopleth. Isopleth is a plotting of radiation heat transfer, and I'll show you a couple of those. But you don't want to be downwind of a gas leak or downwind of an LNG spill. You want to be upwind of it. And I'll show you why momentarily. So let's say we did an isopleth for this spill. Well, it would show you a circle that says, okay, if you're anywhere within this range, you're safe. And but not if you're here, really. So you got to know your wind when you're in an LNG facility. And I know one person who was doing an experiment, and he was downwind, and the flame was over his head, and he said, "Wow, I gotta rethink the experiment that I'm doing." So this was, and you could see how knowing your wind becomes extremely important. Always keep your eye on that windsock when you're in an LNG facility. And vapor and flame characteristics. Now, if a vapor cloud, let's say this cloud goes all the way out over here and gets ignited, you'll see the vapor cloud get ignited here, and then the flame move on back until it's right over the pool. That's a deflagration, means it's a slow burning flame front that starts at one point and then carries its way back to its source of LNG. And you can actually have, if the wind is strong enough, you'll actually have the flame over here, and if the wind is, let's say that's the same velocity as your laminar flame speed, you'll have a flame over here and a vapor cloud over here. Your flame will be staying behind. So you know your wind direction. A lot of what we do in the gas industry is purging out things to be safe. In other words, if you get enough oxygen out of a vessel, and then you have some gas in the vessel, and there's very little oxygen in the vessel, you strike a match, nothing happens. There's no explosion. So you do purging, and there are ways to do purging. The most convenient way to purge is, well, if I have to get this vessel emptied from whatever's in it, I move this, get this vessel emptied from whatever's inside of it. If I put a liquid in, I'm going to do a displacement purge and get all of the vapor out. But they can't really do that with LNG because if you're going to put LNG in this tank, because that water will stay behind, or you'll get some water vapor left behind that will crystallize within your LNG. So we have to use a gas. So typically we use nitrogen for purging. And you use nitrogen, it's a lot harder to purge with nitrogen because you have to depend a lot on diffusion. Now you can trick the natural gas by making this cold nitrogen, but you have to be careful that you don't make it so cold that, let's say you're trying to push air out of this tank and we want to put inert nitrogen in here, make it too cold, any water vapor that's in the air will drop out as liquid. So you want to make it first warm nitrogen. When you get a layer of nitrogen, then you can start coming in with cold nitrogen to try to get a displacement purge. And what you want to avoid is channeling. Channeling is when you get up here reading a good reading. You say, "Hey, I got all the gas, I got all the air, all the gas out of my vessel, and I'm ready to now bring in my other component." Let's say the vessel was filled with air, and I want to now, because I just constructed this vessel, and I want to now bring in natural gas. Before bringing in natural gas, I push nitrogen through here. I take a measurement here, and I say, "Okay, I'm coming out at let's say 95% nitrogen. Good, I'm all purged out." In reality, over here, you might have 10% oxygen. And here you only have 5% oxygen. You think I'm fine. But over here, you might have 12, 13% oxygen. So what you do is you stop your purge, wait for diffusion to take place, then restart your purge and recheck your composition. And one of the problems is that perlite, which is one of the insulators that we use in insulating the tank, well, that acts as an adsorbent, adsorbent, which means it's got many small crevices. And adsorbents are used intentionally to remove water vapor from gas molecules. But also, perlite which is not intended to be an adsorbent, but it's a very good insulator. It tends to capture gas molecules within its crevices, because perlite is nothing more than perlite comes as a solid and then it's heated and popcorned apart into a fine powder. But the powder has crevices that can absorb natural gas. So if you purge out a vessel installation area that's filled with perlite, you have to be careful because you're really not getting all of the gas molecules out. I talked about oxygen and about nitrogen and natural gas as asphyxiants, and the only reason why they're asphyxiants, they are not poisonous, but they are asphyxiants because they displace oxygen. Loss of oxygen content. The first thing you'll start noticing is your cognitive abilities get hampered. Very similar to carbon monoxide poisoning, except that carbon monoxide stays in your bloodstream. But keep in mind something. If you take in a single breath of nitrogen into your lungs are nothing more than a big semi-permeable membrane, a lot of surface area, and it allows oxygen to go from the high concentration side to the low concentration side. So if you take in a breathful of nitrogen, what will happen is not that your hemoglobin will not be getting oxygen, but worse, the oxygen that's in your hemoglobin will leave your hemoglobin and go into that nitrogen. So you actually have a instant collapse. So uh, nitrogen and natural gas, you can collapse. 1979, natural gas, liquid natural gas, seeped through a seal that was in a pump. A pump is nothing more than you have a can that has LNG in it, and it's got a submerged pump in it, and a wire comes out. There's a seal to not allow the LNG to go past the wire, and that wire then goes to your motor control center. And the LNG seeped past the seal and went into the motor control center. And because it's odorless, remember LNG has no odor. The operators didn't smell the bog vapor, and there was an explosion. One person died, and one was injured. Now, talking about oxygen concentration, the air that we breathe is 21% oxygen. If you have excess oxygen, you can have a fire take place very rapidly. And that happened in one of the space capsules where 3 astronauts were killed. They had a very high oxygen concentration in the capsule. A spark started, and the insulation became burned very rapidly. I remember one time as a stupid kid putting a cigarette into a stream of oxygen, and I went like that, and the cigarette literally just exploded. It was incredible, but stupid kids do stupid things. Uh, on a loss of oxygen, if it's not all the way down, you start getting a decrease in motor skills, but worse than that, you have poor cognitive abilities. And you can make really wrong decisions and not even realize you're making wrong decisions. So you have to watch the oxygen content whenever you're in a confined space or whenever there's a possibility that you're in an area that has less than 21% oxygen. The minimum allowed by OSHA is 19.5%. And the cloud is initially heavier than air. Water hammers. You've all heard water hammers probably in a house. If you slam a valve shut real quickly, boom, you hear the piping shake. Well, what's happening? Let's say this is a ship loading line and you're moving many, many thousands of tons of LNG towards the ship or off the ship, and you quickly shut a valve, bam, that water, that liquid has to stop. You're stopping tons of liquid. So you get the hammer packed right into that valve. And due to the what's called the Joukowsky equation, you can get a shock wave that travels backwards back down the pipe, which is at that same pressure all the way back down the pipe to the source. Now it depends on the rigidity of the piping, but that's a water hammer. It's a Joukowsky type of water hammer. Another type of water hammer would be a condensation water hammer. Let's say I'm operating this pipe at 1200 psi. This is a warm dead leg. Well, if it goes to a low pressure, let's say you get an emergency shutdown, all of a sudden this vaporizes. Now I restart the pump up and this liquid starts coming down this pipe and it's condensing this vapor until all of a sudden it hits the end of the pipe, like having a valve that slams shut. You have a condensation water hammer. Talking about stratification next. If I now typically I'll ask a class, I'll say, class, I have an import of light LNG and I have heavy LNG in my tank. Where do I put the light LNG? Meaning density, the light density LNG. Inevitably, most of the class will say you put the light stuff on top of the heavy stuff. Just the opposite. Why? Because you want to put the light stuff underneath the heavy stuff so that it rises up through and mixes with the heavy stuff. Now, here's what happens if you do it wrong. Let's say I put, and this is an actual computational analysis that I did. I took pure LNG and I put underneath it a mixture of LNG and LNG, which is methane and ethane. So I put pure methane up here, and over here I put ethane and methane, 3% ethane, 97% methane. Well, what happens because of the ethane, this is more dense, but it does not mix with this because I put the heavy stuff underneath the light stuff, and it circulates within itself. As it's circulating, what's happening? This bottom layer is getting hotter and hotter. What's happening to the top layer? It's staying at this temperature because it's evaporating at the surface. So that evaporation is keeping it cold. So this density stays the same. But this, as it gets hotter, it expands. As it expands, its density drops. And all of a sudden, I have a condition where I have a lighter LNG underneath a heavier LNG. I get this rapid mixing and a tremendous amount of boil off as this relatively warm, see how temperature here. This is a relatively warm LNG. It's at minus 246, whereas the LNG that we started with was minus 257. So this is minus 257. This is minus 246. This warm LNG sees the surface right here and starts to boil off very rapidly. Now, your tanks typically have relief valves on them. You don't want them to blow, but the relief valves are typically set for, by code today, if you're building a tank, they have to be set for 60 times your normal boil off. Older tanks have only 30 times your normal boil off. In the UK, even though the code may say 60 times, they build it up to 100 times your normal boil off. But in reality, and the two most famous rollover occurrences happened, one in La Spezia, Italy, and the other one in Parrington, UK. They had well over 180 times the normal boil off. And the only reason why I say well over that is the gauges were pinned and they really couldn't tell whether how much far beyond that they went. So you have to be very careful to avoid stratification. If I ask you a question about stratification, what can stratification cause? It can cause a subsequent high amount of boil off, and it can also cause what's called this phenomena, which is a rollover. And it can happen two different ways. You can get a fill-induced rollover,
Fucking God,
where fill-induced
fuck
rollover,
you.
somebody's talking in the background. Please keep it down. or mute your mic. Um, you can get a fill-induced rollover where you put, like we said, a heavy LNG under a light LNG, or you put a light LNG under a heavy LNG, and the rollover is what follows. Now, one of the things that happens in a rollover is a runaway case, because as this warm LNG starts to rise, it starts to boil, and then this bulk density becomes even lighter. And as you can see, it's almost like a geysering effect. It'll really cause this bottom LNG to rise to the top very quickly. Now, no one really knows whether it flips or whether it mixes, but we do know the end result. And by the way, I didn't say what these pictures on the side were. These are just random pictures that I took off of the internet, off of Google Earth of LNG facilities, different LNG facilities. There are three types of tanks that are used to contain LNG. One is what's called a single containment tank, and that is nothing more than an open bucket like this of a cryogenic material. Typically, it's either aluminum or 9% nickel steel. Majority of the tanks are 9% nickel steel. There are some aluminum tanks out there. I've worked on them. And in here is where that perlite lies. It's in here. It's an insulation. Underneath here is foam glass, but it's got to hold up got to be strong enough to hold up the tank. And in here is perlite, and across the top is typically perlite as well. Now this allows the vapor though to get in here, so that this is a pressurized part of the vessel as well. And whatever the pressure is here, pressure is the same here. There are vents through here that allow this pressure to equal that pressure. And this is your single containment tank. Why is it called a single containment? Because this outer tank doesn't contain anything because it's carbon steel. If the LNG hits it, remember what happens to carbon steel? It cracks. So if you have an inner tank break, the outer tank will automatically break, and you're required by code to have an impound basin around the tank. That's a single containment. A double containment tank is you have a wall real close to your tank. I say real close, it might be 6, 7, 8 feet, 10 feet, something like that, but it's close to your tank. And if you have a spill, your vapor will still release to the atmosphere, but you have very limited amount of liquid that's that's in contact with these hot surfaces. Here you have a tremendous amount of surface area, and you get a tremendous amount of boil off. Here you get a much smaller amount of boil off. And then a full containment tank is as shown here, where both the inner and the outer tank are cryogenic material, will be able to withstand cryogenic liquid without spilling. So in a full containment tank, neither the vapor nor the liquid will be spilled. What is the amount of liquid that boils off in a tank? Important question, because you might be asked it. It's 18% a year, 18.25 if you calculate it based on 0.05% per day times 365, gives you 18% per year. So let's say I fill my tank up to 100% full, and you never get to 100%, up to 100% of its working capacity, and because you never bring it up to the brim. You have a certain cushion amount here. And that's for seismic reasons as well as other reasons, which I'm not going to get into at this time. It would be too complex for this level of class. But once I get into this situation, I come back a year later and I find I only have 82% of my LNG. What happened to it? It boiled off during the year. That's something to keep in mind when you consider uh, a peak shaving facility. Now, what also happens is weathering. We don't really have time to get into it, but what happens is the methane preferentially boils off first. So this becomes higher and higher in concentration of ethane and propane. The BTU value goes up. If it goes up too much, You're no longer interchangeable. There are different types of tanks. This one happens to be a single containment tank. You got the tank, and then you have the outer dike. This one happens to have two dikes. It chose to put two dikes in. One dike is required by code. They also chose to put an insulating concrete in here. Why insulating concrete? Because if there were a spill, and this was to fill up with LNG, less heat would go into the LNG. Less heat means less vaporizing, which means less of a vapor cloud that's going to leave the tank area, maybe leave the property as well. What is this? Oh, there are some tanks, not too many, but there are some tanks that the annular space I said was filled with gas. They fill it with nitrogen instead. They seal, go back one if I can. They seal this gap between here and here and fill this annular space with nitrogen. And it has in it a breather tank that has nothing more than a rubber bag in it with a weight on it that just keeps a positive nitrogen pressure on this. And why do you need this? Because the barometer changes. As the barometer changes, you need to make up or take away nitrogen from this annular space to account for barometer changes. These are full containment tanks. So these concrete tanks can hold LNG as well as the inner tank, which is made of 9% nickel steel. I worked at this plant as well. This can hold, I worked at the other plant we just looked at as well. These can hold your LNG inside the inner tank. If the inner tank were to fail, the outer tank holds LNG. There's no berm around these tanks. These because they're full containment tanks. So let's talk a little bit about the construction of an LNG tank. You have this inner tank shown here in I'm looking at a single containment tank in red. That's what's that made of? 9% nickel steel. It actually has a slight dome in it. It's a little bit higher in the middle than on the end. At least the new tanks are. You have a way to put LNG into the tank. You have a way to take vapor out of the tank, etc. When you're dealing with LNG measurements, you have to be careful to make sure you're dealing with making sure that the instruments are reading correctly. So you wouldn't want to take a manometer and bring it inside a room because it's cold outside. So you bring it inside and close the door slightly, and it's a pressurized room because your manometer would be reading it. You want to be careful of false reading. You have a little liquid leg in your line, you're not going to read properly. So this is important when you're commissioning a tank, very important. Because if you pressurize this, the tanks, think of a soda can. Soda can hold quite a bit of pressure. But if you have an empty soda can and you squeeze it, it crushes like a water bottle, a plastic water bottle. Same thing. Well, all of these tanks can hold pressure fairly well, but cannot withstand the vacuum. So you have to be careful that your outer tank never sees a vacuum. Also, you have to be careful that your inner tank never sees a higher pressure on your annular space than in here. So when you're purging out an annular space, you want to be careful to always purge by pressurizing the inner tank and then taking the purge gas out the bottom here. This way you don't end up having this crush. Now I show a green layer here. What the heck is that? That's fiberglass. Now why would I put fiberglass and then perlite? Well, the simple reason is when you cool down this tank, its diameter shrinks by about 6 inches. On a large tank, your tank actually shrinks as you go from ambient, which is 60 degrees Fahrenheit, down to minus 260 degrees Fahrenheit. Your tank actually shrinks in size. So you want to make sure that if you have to uh, or do work on it by decommissioning the tank and do some work on the inside and then recommissioning the tank, that it has somewhere for this inner tank to grow. If this was filled only with perlite, the inner tank would grow, 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 and then buckle because you can't compress perlite, but you can compress fiberglass. So that fiberglass just acts as a cushion so that if you have to decommission the tank in the future, it can grow and then you recommission it and it shrinks again. That's what happened. Or that this is a tank size. When you cool it down, it shrinks. When you heat it up, it grows. When it grows, you want it to be able to compress something. It compresses the fiberglass. Barometric pressure, very real concern that very few people have too much knowledge of. So I use the analogy of a spaceman. And if I have a spaceman in a spacesuit and I keep him at 16 pounds per square inch absolute, I bring him out into outer space, the differential pressure between his spacesuit and the outside world is 16 psi. If I bring him up on top of Mount Everest, and Mount Everest is 4.5, 4.4 psi absolute, his spacesuit is still at 16, but the differential pressure is now 11.6. If I bring him here on Earth and my barometer happens to be at 14.7 pounds per square inch, my differential pressure is 1.3 psi. He's still at 16 psi. He doesn't know anything happened. If I bring him into the lowest recorded pressure on Earth, which is in the eye of a hurricane, and that was at sea level, it was minus. They were down to a absolute pressure of 12.8 psi absolute. Whoops, should have done that. And that would be a differential pressure of 3.2 inches of, not inches of mercury, 3.2 psi gauge shown here. So you see what's happening. The spaceman doesn't know anything has happened. He's gone through all these different places. If I bring him up to a place where the highest recording barometer is known that has been recorded is 15.7, that was somewhere in Siberia. The differential pressure here is only 0.3 psi. You see what's happening? The barometer is changing, or the outside pressure is changing. The inside pressure is not changing, but the differential pressure is changing. Well, what do you think the operator inside the control room is reading? He's reading the differential pressure. So he's got to monitor this. Now, let's say he knows a hurricane is coming in tomorrow. He wants to pump down that LNG tank, get the pressure way down, because when the barometer goes down, he wants to be able to not overextend the tank pressure, the differential pressure from the inside of the tank to the outside of the tank. So let's do this with an LNG tank. Here's an LNG tank, 14.7. He's got a 1 point, and let's say I try to maintain this at 1.3. If I try to maintain this at 1.3, this is now at 16 psi. If now the barometer drops real fast, I gotta pump out enough boil off from here to get this down to 14.1. You might think that's easy, but it's not, because keep in mind, the lower this pressure, the colder this LNG gets. The colder the LNG gets, the lower the pressure, the more boil off, more liquid that boils off. Where does refrigeration come from? It came from boiling off the LNG. And if I go to a high pressure, I now have to stop taking boil off out and let the heat leak bring that pressure up. Now, if I'm getting myself in a situation where I don't have enough boil off, there are safeties associated with that. There are safeties associated with both directions, too much pressure and too little pressure. We'll talk about that, but let's first talk about the construction of an LNG tank itself. I already mentioned the perlite, which is shown here in orange. I mentioned the fiberglass, and I mentioned the inner tank of 9% nickel steel. If you have an old tank, you'll have a bottom penetration where LNG is taken out of the tank. If you are required to open the tank for some reason, you're required to now put in an internal tank valve, which is a valve that can be shut from up top. Keep in mind, the old tanks that don't have these, if you have a break in this line, there's no way to stop the LNG from leaking and filling up your dike. Now, it's on top of foam glass, and the reason why it's on top of foam glass is because foam glass can withstand the heavy force of this LNG. How much is the force? It's about 3,000 pounds per square foot on here. So you got to think about that when you're looking at your geology and thinking about what you're going to put your LNG tank on, the type of soil that you're going to put it on. You have footings, of course, shown here. You have a secondary footing and these have hold down straps to hold your tank in place. your outer tank and your inner tank. And those hold down straps have to be able to withstand the shrinking of your tank as well as the growing of your tank. So it has to be designed. You notice the hold down strap isn't here, but it's way up here. This way, as your tank grows and shrinks, it's able to accommodate that growing and shrinking. There's a little bit of sand in here between your inner tank and your foam glass, because don't forget, you got to weld these plates together. These are lap welded, and these plates are butt welded. And you also might have a top fill. Now, some tanks only have a bottom fill, some of the real old tanks. That's not a good situation because remember we talked about stratification. But the newer tank would have a top fill, which would be LNG coming in, hits a splash pan and sprays across the top of your tank. It also has a bottom fill where you go into a funneled pipe and then it lets the LNG go on the bottom. Now there's a funnel here that if there's any vapor in here, it breaks away from the vapor, called disengages from the vapor, and then the LNG just comes down here. But there is a problem with this design, and I don't have the time to get into it, but if this is a very light LNG, think of what happens. This level of head is the same pressure as this level of head of a dense LNG. And if you, as you're filling, you can actually overflow that funnel. That's an issue that they realized after construction of this type of tank. And then of course you have the vents. There are multiple vents that allow this pressure to communicate with this outer tank. One other thing I'm showing here is heating cables. Why do I have heating cables? And the way the heating cables operate, the heating cables go like this, through here, through all these conduits. Because if you don't put heating cables, remember, heat's going to come from here to here, from here to here, all year round. And you start forming ice underneath here, and you can get frost heave, which can damage your tank. So you don't want frost heave, and these heating conduits are on 24 hours a day, 7 days a week. Now, I say they're active 24/7. They may be on or off, depending upon what the temperature is here. Let's say you have it on an on-off thermostat. It comes on, heats to a certain amount, comes off, comes back on, comes back off. Same way the thermostat in your house comes on and off. However, they found that there's a poor way of managing the heat because it it allows the wires to chafe as they go in and out. So they don't typically uh, they've changed it to a modulating on the newer tank to a modulating voltage, which gives you modulating amperage, so that they basically stay at a fixed rate, no stretching and no heating and cooling of the wires, which cause chafing and cause the insulation to then break down on the wiring as it rubs at the edges of the conduits. I won't go over this because this is just an explanation of what we saw. This is a tank. These are two tanks, actually. It's an import terminal. In fact, I live about a mile away from these tanks. I took this picture myself. And this is an import terminal that was completely constructed in 1974 in and the operating permit was pulled in 1975. The first commissioning ship was en route to here. There's a ship filled with LNG cargo, was en route to this location when the city of New York pulled the operating permit from this facility. It never saw a drop of LNG. Now, this facility in today's dollars would have been about, now I'm guessing at the number, maybe $6 billion with a B. And it never saw a drop of LNG, and they still stand today because these walls were made to withstand a 747 at 200 knots. These walls were made of reinforced concrete, where they wrapped wire cable around and sprayed gunite as they wrapped the wire cables around, and they got insulation. And so these the walls and stuff, you're not going to take these down very easily. It's not very expensive real estate, but again, you're not going to take them down very easily. This is the way a tank normally circulates. You have your LNG, gets a little bit warmer as it touches the wall, comes to the top, evaporates, gets colder, becomes more dense as it becomes colder, drops down down to the bottom. That's a normal circulating tank. And this is what you're striving. A deeper focus on LNG safety. Anything you get on the internet, you have to wonder about its credibility. These, one of these immediate shutdown. Because as soon as there's rupture, gas is detected, every valve shuts. You pent up pressure in vessels and piping. So what you see at first is a mechanical explosion. No chemical explosions, no ignition yet, but there's a shock wave associated with that mechanical explosion, which you'll see when the shock wave comes before the actual uh, smoke and gas and actual before the flame. Now you'll see ignition take place, and you'll see the shock wave in the camera shade. It's coming, it's coming, it's coming. It's a camera shade. It's a shock wave is hit, but you notice now the flame front is coming. So what's happening is, see this person down here. That's why it's important the way you PPE, personal protective gear. That's typically uh, it's very uncomfortable to wear some of them, but because they're quite heavy, they're fire retardant, they zip up. Most times they cover rolls, which are quite uncomfortable to wear, but they're certainly necessary. I'm trying to get rid of this, so let's see if I can get rid of this. Let's see if I can get to my next slide. Screen sharing has stopped. I made a mistake here. Let me go back to sharing. And how do I get this? I'm back in business, I think. Okay. Let me see if I can get out of this. My next slide. Oh, many different process safety analyses are done when you're building an LNG plant. You do a hazard, which is a hazard identification, HAZOP, which is a hazard and operability study, a LOPA, which is a layers of protection analysis, peer review. Many different PSAs, process safety analyses, are done. The company had an excellent safety record. One of the companies I studied had an excellent safety record, yet some, I think it was 15 people died in an accident. And then when I dug further, I found out that they never counted deaths in their accident because it wasn't, there was no lost time accident associated with the death. It was a death on the job. And this was the Texas City refinery, and there's a video out on that. I would and I would encourage you to watch that video. 55 minutes long, but it really gets down to the root causes of accidents that I've seen in my 50 some odd years of experience. In order to get an explosion, you need three things: heat, fuel, and oxygen. You might get a question on this. Just remember, heat, fuel, and oxygen. Those are the three things that are required for a fire to occur. So here's a scenario. You're on shift. You're the chief person in charge. It's 2 a.m. in the morning. Outside temperature is, can't see it. I have to move. I can't see what it is because I have to, okay, 0 degrees Fahrenheit. I have to move my picture off the screen. Okay. Send out is in progress and it's needed. What's send out? You're sending gas out. LNG storage tank pressure is continuously rising, 1.2 psi. Okay, so you see it's rising, so you put on your more boil off compressors. You start taking gas out of the tank, but the pressure is still rising. At 1.7 psi, it's still rising, and you have no way of getting that pressure down. What could be causing this? I'm not going to give you an answer. There are many different answers. We studied rollover. You could be having a rollover take place. There is a vacuum breaker called cover gas, which is connected to your tank that says if your tank ever sees low pressure, it puts gas directly into the tank. Or maybe that's open. There are many different things that can cause this overpressurization. You could have a cold spot on your tank. You could have gas that's LNG that's leaking out of the inner tank, touching the outer tank, creating boil off, and you're getting boil off in that annular space that's occurring. There are many things that can happen, and I'm not going to get into delving into this, but this is the kind of things that you need to think about ahead of time. What will you do if that happens? LNG is very cold. I one time was making up a fitting, and I had gloves on, and I knew I was getting burnt because the cold liquid was coming out, and I kept making up the fitting. I made up the fitting, and then I took my glove off. I looked at my finger, and I said, "That doesn't look like it's supposed to look," and it was hurting. But when you first get a cold burn, because you get that numbing effect, it's not as bad. Eventually, that area of my skin started getting dark, and I didn't want to say anything to anybody, but I went to the doctor. The doctor said, you're lucky it didn't go all the way around the finger because you compromised the blood vessels in that section of your finger. It'll heal. But if it had gone around the entire finger, you might have lost the finger. So you got to be careful with cold. Cold LNG can burn. Now, typically you get some splashed LNG, which just feels like little hot pinpricks on your arm or something, or on your hand. But if you get any serious amount of exposure, you can actually die from it. I know of one person that did die from it in I think it was Algeria, it was a foreign country. With him, what happened was a valve burst and all the product dumped onto the person, and he was killed by the cold exposure. You can also be concerned about the cold weight that's caused by icing on your piping. Also, uh, hypothermia. If you're in an area where it's too cold, your body can become hypothermia or experience hypothermia, where your body temperature drops significantly. One of the major places where you get hypothermia has nothing to do with LNG, but it has to do if you're working on an import or export terminal and a person falls into the water. Well, in midwinter, that person's exposed to hypothermia. The water's cold. Now they typically have a boat that's always in the water that can pick up anybody that was fallen. Typically, anyone also who is exposed to being near the edge of the water has a harness on them with a rope. So there are a lot of precautions, but it has happened where people have fallen into the water. Combustion. Let's talk about what happens with combustion. Let's take CH4, which is methane. There's one carbon atom and four hydrogen atoms. The hydrogen are the little blue guys there, and the carbon's the black one in the middle. Now, it meets up with two oxygen atoms. Molecules, I shouldn't say atoms. It's actually each molecule has two atoms. So it's got O2 and O2, two oxygen molecules. And what happens is it produces CO2 and 2H2O. So the products of combustion are CO2 and water vapor. And actually, in some of the vaporizers that are water bath vaporizers, you products of combustion are bubbled up through the water, and the water level inside the vaporizer keeps increasing and it increases, and then it overflows, and you have to treat that water because it becomes acidic. Why does it become acidic? CO2 and water gives you carbolic acid. So the two form, and you have to treat that water to get rid of it. But what I'm trying to point out here is that CH4 and 2O2 gives you CO2 and H2O. Let's say I have a fire in progress. How do I stop that fire in progress? Remember, we have three things. We either eliminate the oxygen, eliminate the heat, or eliminate the fuel. One way to start, we shut the gas off. Another way to stop it would be stop this heat transfer. Another way because keep in mind, this heat transfer is what ignites the next set of molecules that are sitting over here. And that heat given off by that is what ignites the next set of molecules. So one way you can do that is if you have enough purge gas in the way. Let's go. I'm not going to go back one. Let's say I put enough purge gas in this vessel, and although I have gas in the room, let's say I'm in a room right now, and I have 3% gas in the room, gas and air, and I strike a match, nothing's going to happen. The flame will not propagate. Why? It's too lean. It's too lean. I'm in the 3% range. I'm down here. This is the room with no gas in it. As I add gas to the room, I'm getting less oxygen in the room. Get to a point where I get to here, I'm at the lower explosive limit of that gas, of that mixture. So at the lower explosive room, where I light a match, boom, I get an explosion. All the way through here, I'm up at 10% gas and air. That's about the stoichiometric mixture for gas and air. Up here, I'm at 15% gas and air, somewhere a little bit higher than 15% gas and air. I could still strike a match and boom, there'd be an explosion. Up here, I'm at 17% gas and air. Strike a match, nothing happens. Why? There's too much fuel. Now that sounds a little contradictory. Too much fuel. Well, what is the fuel? The fuel is an insulator. It insulates that heat from being transferred to the next set of molecules that are ready to combust. In the same way here, there's too much air in this room for the heat to transfer from that first set of molecules to the next set, so the flame does not propagate. But anywhere within this red zone is a flammable zone. So let's say I have a vessel, a large vessel, let's say it's an LNG tank, and I want to bring it down I want to purge it out. So I bring it down to 9% gas and air, 9.5%. Typically, they bring it down 9.5% gas and air. So I'm here at 9.5% gas and air, and as I add fuel to that tank, I never go through the combustible zone, and therefore I never have any concern about combustion. This is what actually happens here. I just added enough nitrogen, 9.5%, and then as I added gas to it, followed this path, never got into the flammable zone. And that's how you purge out. That's how you would gas in a tank. Now here I went up to, this is combustible volume. Here I went all the way up to 100% gas in the tank, and the tank is ready to be brought into service. Now, you always bring an LNG tank, you always product purge it by bringing gas into it before you bring LNG into it. Deflagration and detonation. Deflagration is a slow fire that burns at below the speed of sound. So you can light the fire, like I said to you, if you had a pool here and this long cloud of vapor going off. You light that vapor, and the flame travels back to the pool of liquid. That's a deflagration. A detonation is where you have, let's say, gas and air in a room. It's a confined space. You light it, bada boom, you have an explosion. Or if you have if you add a lot of turbulence to the fuel mixture, you can end up with a detonation because you have your flame front has a large surface area. In fact, I did my PhD dissertation on flame propagation within internal combustion engines using methane as a fuel. And a lot of it had to do with how much tumble and how much swirl you put into the combustion chamber. And those are different types of turbulence that you put into the combustion chamber. And if you do it high enough, you'll get a detonation. Do it the right, just perfectly right, you get the right level of deflagration, and that's what you want in a combustion engine. A detonation can occur from LNG vapor if the vapors are contained, like in a house or a substation. A detonation can occur in a very crowded pipe rack. If as the flame occurs, that all that gas is being pushed around pipes and you get a lot of turbulence, and you can get what's called a deflagration to detonation occurrence. So it starts out as a deflagration and then it degrades further and becomes a detonation. Now, this is the steep plant in Algeria. Now, this was called a deflagration, but it sure as heck looks to me like it was a detonation. And originally what happened is MR, which is mixed refrigerant, leaked into the inlet air of a boiler. and the boiler overheated and exploded. That in turn took out some piping, which was carrying gas, and ended up having a follow-on pipes that exploded. I got to be careful about the words exploded. The boiler exploded, breaking other pipes, because explosion implies detonation. They declared this a deflagration, but when the boiler exploded, I'm having a hard time calling that a deflagration, because the boiler is literally a steam boiler. So that breaking of the boiler by overpressure could have been an initial detonation. But this is the end result. Why would this not happen here today in the United States? Because we require that every furnace or every boiler at the intake of a boiler, go to any boiler in an LNG facility and look at the intake air, and you will see a device there. That device is a gas detector, and that's tied into an automatic shutdown of the boiler. This plant did not have that. Should it have had it? Probably. It was one of those things that wasn't required when the plant was first built. It was required after the fact. It was probably on the punch list to yet get done sometime in the future. They have a lot of what's called MOC, management of change, changes that need to be made to the plant. Keeping up with your MOC is important. This might have been on the MOC list. Obviously, it wasn't done. Now, this is a detonation. Put it this way: this appears to be a detonation. I took this off the internet, and like I said, what you find on the internet, whether it's true or fictional, I don't know. But the reason I took this off here was because it does show pretty clearly the what happens in a detonation. I want to play it here so that I can switch to the other slide without losing my internet, without losing my connection. Now, playing it here, and you're going to see an explosion take place. Okay, explosion has started. What I want you to do is watch this building. Before the explosion gets there's a shock wave that hits that building. There it is. Almost. Almost. There it is. You see the shock wave hitting that building? The explosion hasn't hit there yet. The flame front hasn't, but the shock wave has. And this would be a detonation. You can see what's happening, how this is all being blown apart. When you look at movies of wars and stuff like that, here, you can see that shock wave hitting. When you look at now the shock wave has hit the cameraman, so that finishes that. Okay, let me go to the next slide. Let's see if I can get big screen again. So what happens with a detonation, you get that shock wave. Now, if you look at war movies and you see bombs dropping, you see boom, there's a small explosion. And if you're looking from the plane's view, you see a small explosion. Then you see this wave that goes way out past the explosion. That's a shock wave. And the amount that's the shock wave that causes death and destruction. If you experience a shock wave of more than 1 psi, not PS, 1 psi, that's pretty well detrimental to internal organs. Once you go above 1 psi, the lungs, liver, etc., get that bam effect, and that's what can certainly kill you. You don't have to get hit by shrapnel, the detonation alone. This just shows you some oxygen contents, and we've gone over what they would be and when they would be. So this is something that you just look at and say, okay, I understand when I'm going to. The only place I'm going to get that fire is when I'm in the flammable range. Now, talk about flammability range. The two fuels that concern me the most are hydrogen and acetylene. And I've experienced explosions of both of these. Hydrogen, when I was a kid, I was trying to do welding. I didn't know how to weld. I just saw it and I said, that sounds fascinating. So I got a bunch of lead acid batteries, put them together, the car batteries, put them together, got a piece of steel and a coat hanger, and I kept making an arc, trying to weld. And eventually the batteries were discharging and the hydrogen started producing hydrogen in the batteries. Hydrogen ignited, blew the battery up. I got all acid sprayed in my face, and fortunately the batteries were dead enough that I was able to. Well, I tried to run into the house, but I ran into the brick wall because I couldn't open my eyes. Eventually, I found the door, found the sink, got my face washed off and everything, and got in trouble afterwards. And acetylene happened on a job where I had two workers working, and they put the acetylene torch inside the cabinet on the side of the truck, and they left the valve on the tank open. And this was their own way of operating. They had made a hole in the side of the truck, had the acetylene tank in the open part of the truck, and then had the hose go into the closed cabinet and rolled up the hose, put it in there, slightly leaking. As the person was grinding the pipe, spark went by the door of the truck and blew the side cabinet right off the truck. It tore the muscle out of one guy's arm. He was permanently disabled. Tore the muscle out of the other guy's leg. He was permanently disabled. I remember visiting them at their house, and the door kept on going and dented a metal basement door, and it certainly gave me a realization of how serious acetylene can be. A very, very wide range of flammability. Now, natural gas, remember we said was 5% to 15%. This is 2.5 to 81. This is 4 to 75. Very wide range of flammability. Now, these are isoplets. Now, realize isoplets are radiation zones of thermal energy. Let's say I have a fire here, and I do my computations, and this is how many BTUs per hour per foot squared. This is how many BTUs per foot squared. This is how many BTUs per hour per foot squared. Keep in mind what I said about the wind. This does not take into account the wind. So in the ideal world, all flames point straight up, and all flames have isoplets that can be calculated living in the real world. And we're not, the picture you see is not the real world. The picture you see is done by calculation. Radiation decreases to the fourth power, to the squared power by distance. So here you have a radiation value of, let's say, 1, here it's 1/4, here it's 1/9. So the further you get away from a flame source, the better, and it's not a linear relationship. You get twice as far, you only get 1/4 of the radiation, 3 times as far, 1/9 of the radiation. So distance is your friend to radiation heat transfer. But what can radiation heat transfer do? Now, what's not taken into account, you remember seeing that explosion in the petrochemical plant? Uh, it does not take into account the initial explosion, all the debris and shrapnel that comes off that explosion, does not take into account the initial gas release. It takes into account only the steady state release of gas, the steady state. So if you have, let's say, a pipe explode on the ground, it ruptures. It's not taking into account the Edison rupture. Made a crater that was 65 feet wide, 140 feet long, 14 feet deep. So it doesn't take into account all the debris that was blown out of the ground or the initial blast. It only takes into account the steady state flow of gas. So this is from the GRI report that talks about where a lot of the rulemaking was made. It talks about the steady state flow of gas and the radiation related to that, the heat radiation. So this is 1600, and in 30 seconds you're at the threshold of burn. This is 2000, and here you're at the threshold of blistering. 3,000, let's go down to 5,000, 30-second exposure. You're at the point of a 1% mortality. This doesn't mean that, only 1% of the people were hurt. It means everybody got burned, but 1% of them were burned bad enough that they died. And this also, if you read the text that involves in this, it says the person is a fit person, physically fit, that's capable of running 200 feet to a shelter and find shelter within this 30-second period of time. So those people that are fit enough to run, they were not hurt by the initial blast, they're fit enough to run, and they got to a point of shelter, and they still did get burned. 1% of them had a mortality of 1% died from their burns. Now, if you go to 8,000 BTUs per hour per square foot, this increases to 50% mortality for 30-second exposure. If you go to 12,000 BTU per foot per hour per foot squared, you go to, in 30 seconds, 100% mortality with spontaneous combustion of the clothing. So these people did get to a shelter, and 100% of them died, and they may never got to a shelter. 30 seconds of exposure, they spontaneous combustion of the clothing and severe burns and death. 100% mortality. So here's just that plotted on a graph. Plotted on a graph. So let's say I want to place a LNG facility on a site. So I got this great idea. I happen to have a couple of $100 million and I want to invest it. And I said, I'll make an LNG plant. I'm going to put it here in this location. Well, I'm certainly not going to put it in New York City because it's not allowed in New York City. And New York City in 1974, 40 workers were killed in an LNG tank, and it was deemed an industrial explosion. But they were working in an LNG tank. It was a full containment tank. They had a deflagration inside the tank. It pressurized inside the tank. The concrete roof raised up and then collapsed in on the workers. Now, the tank had not seen a drop of LNG. It had been purged out for 10 months prior to this event. And what happened is you saw the tanks that I showed you earlier. Those were about 3 miles away, the tanks that never stored a drop of LNG. So the tank that blew up, of course, they took out of service. They bulldozed the place. You drive past it today, it doesn't look like the tank was ever there. The tanks that was 3 miles away, they withdrew their operating permit from those tanks. And so LNG was banned in New York State up until 2099, from 73 to or 74 to 2099. And even at then, it was banned after that because it wasn't until 2015 that they then put in place rules that allowed the building of LNG facilities in New York State, but not in New York City. New York City, you cannot even transport LNG. Not that LNG is not safe, but it's got perception of having issues. And we talk about two types of spills. You have a design spill, which is defined here, and I'm not going to get into it, but it's a certain amount of spillage based on the type of tank you have. Typically, it's a 10-minute spill. Unless you have no internal tank valve, then it's a continuous spill of whatever's in your tank. And there's two types of there's two types of confinements or a spill amount. There's a design spill. I went backwards on the slides. And then there's a full impoundment spill. So let's say a design spill is a certain amount of LNG that's spilled out by that definition. A full impoundment is the dike that's around the tank being full with LNG. So this one is a full impoundment, this one's a full impoundment, and this one's a full impoundment. This one's a design spill. And they give you what's allowed in radiant heat flux. So let's say I'm going to build a facility and I have at my boundary line of my facility a point that has 1,600 BTU per hour per foot squared. Exposure, a property line at ground level that can be built upon for ignition of a design spill. So I compute what a design spill is, and I said, is there property outside my boundary line that can be built upon? That's the key. Now, what about if it can't be built upon, but let's say I have this situation here where I have an impound. This is a full impound tank fire, and there happens to be a facility that's a place of public assembly where 50 or more persons can reside. Well, if that exists, the nearest point located outside the property line at ground level that at the time of plant siting. So in other words, I could build my tank today if nothing is out there. And if somebody builds something 5 years from now, that's their headache. That's how this is written. This is the code. And you have to know which code to apply. The code NFPA 59A has no teeth in it other than the fact that 49 CFR Part 193, which happens to be the federal code, dictates that you have to abide by 59A, but it dictates certain additions. You have to abide by the 2001 edition of 59A for certain parts of the code, and for other parts, the 2006 edition. So knowing which parts, it gets very. I want to get down to some examples. These are two single containment tanks. You can see they're single containment by the fact that they have the berm around them. Single containment has a small impound area. This is for a spill. And you see there's this little green thing here. It's a water pump. You don't want to have water in this area, so if it rains, you pump the water out of the impound area. And if you have a design spill, that spill would come down and collect over here, and you could have a fire in this small impound area. If you have a full dike spill, well, this entire dike would fill up with LNG, and you get a considerable amount of vapor production. But as you can see, there's not too much requirement on the design spill. The codes I mentioned, and you got to be careful because many of these codes within 193, there are many codes that are referenced, including NFP 59A. If you read NFP 59A, you'll find out that many numerous codes are included in there. So let's look about vapor concentration. This is another one, another requirement. And this part of the code says, and this is part of 59A, which is required by 193. And this says that the spacing of LNG tank impoundments to property line can be built upon. Notice that can be built upon, very important. Be such that in the event of an LNG spill as specified in 3.3.3.7, that's the design spill, an average concentration of methane, 50% of the lower flammability limit, that's 50% of the LFL or LEL, they both mean the same thing, does not extend beyond the property line that can be built upon in accordance with a model. And they tell you what model to use for doing that calculation. So this is very interesting here. Based on thermal radiation, can this plant be built if this is an isoplet for a design spill? Well, that's the design spill, is not the full dike spill, but it's a design spill. And if these are my isoplets, the answer is maybe. Now, how do you say maybe? 1,600 BTU is outside the property line. The question is, can this be built upon? Is this an island that's with nothing but water around it that can't be built upon? Is this all wetlands? And then it's really up to the the authority having jurisdiction. So it's AHJ, the authority having jurisdiction. If they don't want you there, you're not going to build that, period, regardless of what the code says. But they can determine, well, this is an island, so you're okay, you can build here. Or they might say, no, you can't build here. Even if your isoplex was inside here, if they say, no, you can't build, you're not going to build. Like in New York City, you're not going to build an LNG plant, regardless of how much of a buffer zone you have. Let's see if I can get to the next slide. And here's the next sign. It says, based on thermal radiation, can this plant be built on if this is an isoplet for design spill fire? I think that's the one we just did. And this one's the next one. Okay. Now we're talking about based on the thermal radiation, can this plant be built upon if it's isoplets for a full dike impoundment fire? For a full dike impoundment fire, what is required? Totally different. Remember, for a full dike impoundment fire, the rules are totally different. Let me see if I can grab those rules. I have them here. Here they are. You are allowed to have 3,000 BTUs per. Okay, the nearest point located outside the owner's property line at ground level at the time of siting is used for outdoor assembly. Well, it really is at the time of siting. If there's no outdoor assembly here, you can build this. 3,000 BTUs. is required that is in existence at the plant site at the time of plant siting and is used for assembly, education, healthcare, detention, correction, residential. 3,000 was all within the property line, so that one doesn't count. So this can be built. This can be built if there's no place of public assembly at the time of siting. See if we can look at the next one. Okay, now this one's very interesting. Very interesting. Watch this closely. This is for a full dike impoundment spill. If these are LEL, remember, LEL is 5% gas and air. So 100% LEL means 100% means 5% gas and air. That's 100 LEL or 100% LEL or 1 LEL is 100% LEL. This could be called 1 LEL or it could be called 100% LEL. Remember, 100% equals 1, which is what? 5% gas and air. 300 LEL, what is that? That would be 15% gas and air. 1,500% LEL, what is that? That's 75% gas and air. Can you build upon this for a full dike impoundment spill? Remember the code said for a design spill, 50% LEL at the property line. Well, this is a heck of a lot more than 50% LEL, but this is not a design spill. This is a full dike impoundment spill. The code is totally silent about a full dike impoundment spill when it comes to vapor generation. It's so unlikely that the code is just silent on it. So if this were a design spill, I'd say, no, you cannot build this. But if it's a full dike impoundment spill, there's nothing. This does not stop you. This particular set of isopleths do not stop you from building because it's a full dike impoundment spill and the code is silent on that. So now let's say this is for a design spill. In this case, your 50% LEL is within your property line. Yes, you can build this. So public and political opinion can be a stronger reason than technical reasons for not building. Think about what happened to the Shoreham nuclear power plant and to the district gas tanks in Staten Island. Those are the ones I showed you earlier that never saw a drop of LNG. Public opposition pushed political opposition, which shut those facilities down. Now, the one thing we did not talk about is LNG is transported by truck. There are tens of thousands of LNG trucks that cross all over the country except New York City. That's the only place that I know of where they're not allowed to travel. And all over the country, they're not allowed in tunnels, typically. I can't say every tunnel has that restriction, but I know they're not allowed in tunnels in general. That's a general rule. They're not allowed in enclosed parking garages for obvious reasons. Now, LNG tanker trucks have to be vented down. Remember, it's nothing more than an insulated tank. And if you drive it a long distance, that mechanical work that goes into the fluid creates boil off and you have to vent it off. So that's part of the concern with an LNG tanker truck. With an LNG ship, you also have boil off. Rather than vent it off, they typically feed it to the boilers so that they use it as fuel. So that's one way. That's if it's a steam-driven engine. If it's diesel-driven, which most of the newer ones are, many of those have been converted to accept a certain portion of the LNG vapor along with the diesel fuel. The diesel fuel is still needed to create ignition because LNG vapor will not reach combustion temperature due to compression in a diesel engine, but a small spray of oil will start the ignition and give you a flame propagation that you can run your diesel engine on natural gas. And that's why I like even natural gas vehicles, buses and trucks. You typically will have a certain amount of diesel fuel that's used for your pilot ignition, and then they're fed natural gas is aspirated into the inlet so that it can burn in the combustion chamber. Okay, one more scenario. It's 3 a.m. in the morning. Send out is in progress and it is needed. Tank pressures have been unusually high all day. The outside operator reports a cold spot and an ice formation on the base of tank number 1. Well, the fact that I'm saying on the base of tank number one implies that you have a second tank or maybe a third or fourth tank. But this is one I just throw out there and it's for you to think about. Now, you can have two different situations. You could have dropping pressure or rising pressure. Question is why? What's happening? Think about your add gas, your cover gas, etc. And I do want to go over some questions to kind of summarize everything we've spoken about. Let's say, for instance, an LNG, and that should give me my closing slide then. Yeah, there's my closing slide. It says thank you. And the one thing I do want to remember you to remember before we leave this session is that Insight place where it should read Insight Engineering, but as you can see, I forgot my R. It's on the ring side of the hub. It's actually InsightEngineeringHub.com is the website. Okay, an LNG inventory stratification can result in what? And then LNG, well, what's going to happen when you have stratification? You're going to get the stratification is going to end up with that bottom layer getting less dense, less dense, less dense, and you get a rollover. What happens when you get a rollover? You get a lot of vapor generation. What type of LNG tank is surrounded by a dike or berm to contain the LNG? Single containment, a double containment, a full containment, a floating roof with a bladder? No, a single containment tank. It's surrounded by a dike. With a full containment tank, if the inner tank were to leak, what would happen? Neither the LNG nor the vapor would be released. Remember, a full containment tank is a full tank within a full tank and where both can withstand the cryogenic temperatures. As the barometer changes, barometer changes affect what? The what? Well, it would affect the LNG boil up in the tank if the tank differential pressure between the atmosphere and the tank is maintained fixed. Because I maintain that differential pressure as the barometer changes, so does the pressure in the tank. And also, it will affect the height that you read on a barometer. As the barometer changes, the barometer reading will change. The LNG at the top of an LNG inventory is what is it? What is the LNG? Is it saturated vapor? Is it saturated liquid? Well, the LNG, the fact I'm saying LNG means it has to be a liquid, and it's a saturated liquid because it's boiling. If it was a subcooled liquid, it would not be boiling. There's no such thing as a supercritical. Well, there is a such thing as a supercritical fluid, but certainly not that. That's over the critical point. And it's not a saturated vapor because it's a liquid, so it's a saturated liquid. That's what's at the top of your LNG tank. When vapor comes off an LNG spill, what is one of its characteristics? It's more dense than air. The convective circulation of LNG in a tank assures that the LNG at the bottom of the tank is nearly the same temperature as the LNG at the top of the tank. Why? Because remember that circulation is going like this, continuously circulating, and that cold LNG at the top, essentially the same temperature as the cold LNG at the bottom. Some process safety analyses include hazard identification study, hazard operability study, layers of protection analysis, all of the above. That would be the answer to that. What happens in a fire above a pool when LNG spill ignites? Well, what happens? Heat energy leaves the combustion process in the form of radiation. That always happens in a fire. And what else happens? Water and CO2 are formed as products of combustion. Anytime you have LNG or methane being or ethane being burnt, you're going to end up with carbon dioxide and water vapor as a products of combustion. What three things are required to result in a fire or an explosion? Fuel, oxygen, and heat. LNG is so cold that coming in contact with it can cause injury. Yeah. Special materials need to be used to contain it. Yep. Ice can form on the piping and vessels containing it. Yeah, of course. All of the above. When mixed with air, LNG vapor will propagate fire, or cause an explosion for which of the following concentrations? They give a bunch of concentrations. Well, what's the stoichiometric concentration? How about 10% methane gas and air? Stoichiometric just means ideal, the ideal concentration where you get complete combustion. Impound areas are there areas where personnel should muster? Absolutely not. The impound areas are areas intended to capture spilled LNG to reduce the associated hazard. Spilled LNG will turn into a cold vapor. The vapor is flammable only when mixed with oxygen. That's obvious. What is the design boil-off rate for a typical LNG tank? 0.15% the tank capacity per day? 0.05% the tank capacity per day? Yes, that is correct. Remember that 0.05%. And if you multiply that by 365, you get the next answer, which is 18.25% of the tank capacity per day, per year. I'm sorry, per year. Well, it's either 0.05 per day or 18.25 per year. And that concludes the class, and I am right on the money timing wise with 1 minute over. So if anyone wants to hang out for questions, I'm willing to take them. But if anybody's still awake, I'm willing to take your questions. Sham, are you there?
Yes, yes, Steve. Any question to Steve, please type it in the chat or Q&A.
I see something in the chat. Let me see if I can open it up. I've not done this before. It says, webinar 6 video, will you able to same page 24 hours after the webinar? Oh, this is your message. Please avoid using Edge or Internet Explorer browser. Okay, this is your message. Thanks for the overview. Thank you. And I see no other comments. If there's any questions, you do have my email address. I on my computer more hours than I'm breathing. So you do have my email address, and you can reach me, and I can always give you answers. If you ever want any, is LPG a related fuel? LPG is really propane, mostly propane. If you go and buy LPG for your barbecue, it's probably 90% propane, some ethane, some trace amounts of methane, some butane, but you're talking about 90+% propane. And the only reason why it's sloppy, it's got some ethane and butane in it because why you don't need to be 100% propane, but it's mostly propane. That's LPG, it's liquid petroleum gas. So it's within the alkane series. You have methane's the lightest, then ethane, then propane, then butane, then pentane, then hexane, then heptane, then octane, then nonane, then decane. That's the alkane series. But LPG is typically the propane and one above and one below, a little bit of each of those. But LPG is made through pressure, I assume, versus LNG is made by cooling. Yeah, what happens is if you take propane and you bring it down to minus 44 degrees, it turns into a liquid. But if you take propane and you put it under pressure, let's say at 0 degrees Fahrenheit, it's got its associated pressure with it. It might be, let's say, 30 psi at 50 ps at 0 degrees Fahrenheit. At 60 degrees Fahrenheit, it might be 100 psi. At 120 degrees Fahrenheit, it might be 140 psi. At 250 degrees Fahrenheit, 250 psi, maybe it's maybe at 150 degrees Fahrenheit, it's 250 psi, which is the relief valve setting typically, and blows your relief valve. So yeah, that's typically it really boils down to what makes it easier to store. With propane, pressure makes it easier to store. So rather than cooling, but you could buy liquid propane at minus 44 degrees Fahrenheit and just be in a container. In fact, many large storage tanks, like the one you see in front of you, are carrying liquid propane at minus 44 degrees Fahrenheit because that's the way they choose to store it rather than at high pressure. It's much easier to store large quantities of propane at refrigerated temperature than at high pressure. But don't forget this, the quantity is very large. Got it. Thanks for the explanation. Makes sense. That's cool. Now, yeah, if you take your propane tank out in the middle of winter when it's 5 degrees out and you go to use it, you see that the flame is quite small. Piece of information. I've had times where it's been 5 degrees or less, and I go to use my propane torch and I'm out of luck.
There is one question in Q&A, Steve.
Let's see. I don't see any more questions. I see thank you for the overview. LP is related fuel. I don't see any more questions. Do you see any? But LP is made of liquids through pressure. Yes, that's correct. It's based on the, in fact, I'd love to, if you had the time, I'd love to show you the curve for LP pressure. I'm going to show you, if you're interested, I'm going to show you a tool. Stop sharing for a moment or try to get out of this. I'm going to start sharing again, and I'm going to go to this program here called RefProp. Share. Okay, I'm in a program now called RefProp, and I'm going to go to options, and I'm going to say units. I'll say English, and I'm going to say substance, and I'm going to say I'm going to pick propane. Substance, propane is here, and I'm going to say okay, and now I'm going to say calculate. Let's say saturation. I want saturation points at equilibrium. Here's propane. I'm going to say, let's say at 14.7. And I see my temperature almost minus 44 degrees. Let's say at 50 psi. And I can see my temperature is now 13 degrees. Let's say at 100 psi. And I see my temperature is 55 degrees. Let's say 150 psi. And my temperature is 82 degrees. So in my propane tank, if it's 82 degrees outside, and let's say I got my barbecue tank sitting on the deck and the sun is beating on it, 110 degrees Fahrenheit. Well, what is look at that. That pressure is up to 214. Let's say I get to 120 degrees Fahrenheit. Oh, I'm very close to my relief valve setting, which is typically 250 psi. Let's say 250 psi. And you can see 250 psi, my LNG, my not LNG, my propane is at 122.5 degrees Fahrenheit. I just wanted to show that. I don't know if anybody's out there, but I thought you'd be interested in seeing that. And you could also plot this if you care to. So, all right. If anyone needs any answers to anything, you have my email address. Have a wonderful rest of your day. And remember, when you need professional engineering, continuing education, Insight is the Insight Engineering Hub. It's a place to go. I'm going to sign off now.
Yeah, thank you all. Thank you, Steve. That will end the webinar. We'll see you next week or whenever next webinar you like to take. Have a great evening.
You too. Bye-bye.